so far, all of our polar regions that we've integrated over were polar rectangles. Remember, polar rectangles are basically built from a polar circle where the r and the thetas are constants. In other words, it's basically built off of a circle centered at the origin. So, but that does not have to stay that way. We do not have to always work with a polar rectangle. So what happens if it's not built from a circle around the origin? What happens if instead of these being constants, so in other words, the r values are not constants anymore, like they have been up to this point, right? We've always had r values be constant for every one of these problems. But what if they're not constants? What if they're functions of theta? Well, that's going to make everything a little bit more work, right? So let's see here. So theta still goes from alpha to beta, right? Because you have to have constants in some portion of this. So theta will be in the constant form. But r will go from some function of theta, right? This inner function right there, to some outer function of theta. And of course, we'll still have our integrand, f of r theta, but times r, right? Because of course that's dA, right? R dr d theta. All right, so let's put this into practice 3 different times. So we're going to do example 6 has 3 parts, and each of the regions is a different zone. And it's always the same as 2 circles, but we're going to use different regions. So the first one we're going to do is this piece over here that's outside r equals 2, but inside r equals 4 cosine theta. Okay, so let's see here. The double integral over the region of 2x will be 2 times the double integral, because I'm just going to bring that 2 out in front. And then it's going to become x, which is r cosine theta. And then dA is r dr d theta. There we go. Right, so these pieces together make the dA, and this is our 2x. Okay, let's look at our region here. So this is a little bit tricky. What might be smart in this particular case is, well, we first need to figure out where they're equal, right? What theta value is this? And then, so we start down here, and I spoke this way, right? Starting at the pole and coming out to that corner, and then it would chug, 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 chug through and end up over here at this theta value. So we need to find the theta values. We need to know where 4 cosine theta is equal to 2. All right, well, let's do that. So 4 cosine theta equals 2 means the cosine of theta is a half. And boy, am I glad I memorized my unit circle, because then I know that theta is one of 2 angles. It's pi over 3 in the first quadrant and negative pi over 3 in the fourth quadrant. Or if you will, it's 5 pi over 3, but we want to go from here to here. So this is negative pi over 3 here, because we need to sweep through and end up over here. So using 5 pi over 3 would not help me, right? So I need to start in the negative and work my way to the positive. Okay, so I'm going to go from negative pi over 3 to pi over 3. Those are my theta values. All right, now what about r? So you have to imagine, again, the spokes coming out of the pole. And r is the different radius values. And in this case, one of them is always the same. It always hits this ring at 2. So I know it starts at 2. So that one is a constant. But this out here is 4 cosine theta. It's a function. Like that. All right, now, there's a couple things here. One, We have theta involved in this integrand, so we will not be able to use our trick. Right, we'll just make a little note. Here, note theta. It's actually in the integrand or in the limits of integration, and it's actually in both in this case. Right, theta. Oh, here, let me put it up here. Note theta is here, so you cannot use our trick. Right, where you just make theta disappear and put in the value. You can't do it. Right, theta is involved in the integrand as well as the limits of integration, so you're stuck. You're actually going to have to do this work. First off. Second off is it'd be nice if we could make this a little bit simpler on ourselves. And we can. One of the things we can do is we can think, look, from negative pi over 3 over pi to 3, then there might be some symmetry we can take advantage of. We'd have to check that the region of the integration is the same. And we'd have to check the integrand, which is 2x, to make sure that it would be the same to use symmetry, right? But it would be. So we're going to make this integral. Let me write it out first, and then let me tell you what I'm doing. So instead of going from negative pi over 3 to pi over 3, I'm going to go from 0 to pi over 3. And then I'm going to leave the rest of this the same. So this is from 2 to 4 cosine theta. This is r squared, right, because r times r, cosine theta, dr d theta. Be very careful. This r is the thing that students are most likely to drop because they lose sight of it, so don't lose sight of it. It's there. All right, so to use symmetry, I'm going to make a little note here. Most of the time you can do it, but not always. You have to check things. Check that your integrand, which in this case was f of x equals 2x, is not affected, right? Is the same, which it is for us, so no problem. And you check that your region is the same, which it is, no problem. I mean, it's not the same, it's that it's symmetrical, right? So we're okay to cut this in half. We're only going to look at this piece of it rather than looking at the whole thing. It just makes the integration a little bit easier to use 0 rather than to use the negative pi over 3. Again, it's not strictly required if you don't want to do it. Now, if you do that, you're going to have to multiply by 2 in front to compensate for the fact that you only did half of the integral, right? So you multiply by 2 to compensate for the fact that you're starting at 0. All right, now let's do this. So this is 4. We're going to integrate with respect to r. So you have to do r first, by the way. You cannot do theta because theta is involved in this integrand. So you cannot do it. You have to go in this order. R has to go first. So this is 4 times the integral from 0 to pi over 3. And then this is 1/3 r cubed. R goes from 2 to 4 cosine of theta times the cosine of theta dr. Excuse me, d theta. Oops, I just did dr. This cosine of theta just sits there, right? It's not really involved because it doesn't have any r in it, so it just sits there. So now I'm going to put 4 cosine theta into that and 2 into that. And for the sake of simplicity, let's also bring that third out. So this is 4/3 out in front from 0 to pi over 3. And then this becomes 4 to the third, which is 64. 64 cosine cubed theta minus 8. All times the cosine of theta d theta. And we're going to make Maple do that. We are not going to do that. All right, so let me kind of segment this off. All right, so let's go see what this looks like. All right, I typed in the original integral, and then I typed in that one after I had integrated, so I can check that my integration step was correct, which it was. And sure enough, there we go. Now, grant you, I distributed in the cosine of theta when I typed it into Maple, but, you know, whatever. It'll be fine. All right, so we get that the answer is about 40.439. So there we go. I'll put an approximation symbol and say 40.439. And if you were trying to find the volume, it'd be units cubed. It didn't specify that this was a volume, so I'm not going to worry about it. Okay, let's take that same polar region and let's do a different section now. So let's do this section right here. All right, now this is trickier than you think. We know that they equal each other at theta equals pi over 3 because we already found that. But we have a problem. If you have a spoke coming out from the origin this way, it's going to hit that ring right there. No problem. 0 to 2. Wonderful. But that only works until you get to here, until you get to that pi over 3. And then for this piece over on the left, a spoke would work differently. Let me do it in orange. It would go from the origin up and would hit right there. Uh-oh. That means we need two integrals. We need one for, and let's see the dividing line. The dividing line is right here. We need one for from 0 up to that piece, right? Up to pi over 3, right? From theta equals 0 all the way up to theta equals pi over 3, right? We need that piece. Then we need another piece over here, which starts at theta equals pi over 3, but ends over here. So we're going to have to find two double integrals. So let's call these sections, if we will. Section A over here and section B over here. All right, let's find the integral for A. Okay, so the integral for A, now this is y squared, and that's not changing. That's the integrand. That's some three-dimensional surface that's above all of this, right? So this is just the region of integration. There's some three-dimensional ceiling that is y squared that we're trying to integrate, right? But we don't care what it looks like. So that is r sine of theta squared. And then dA is r dr d theta. So theta goes from 0 to pi over 3, and r goes, hey, this section's pretty easy. R is going to go from 0 to 2. That's always at 2. So 0 to 2, hey, it's numbers. Woohoo! Right? That's great. Unfortunately, theta is involved in this integrand, so we're not going to be able to use our little trick. So we're going to have to do a little bit of work here. All right, so this is the integral from 0 to pi over 3. And then I'm going to write this integral again, 0 to 2. And then I'm going to simplify this. This is r squared times r, which is r cubed times the sine of theta, dr d theta. This is one time where actually you could reverse the order. If you'd rather integrate sine instead of r, you know, whatever. Because all of these are numbers, it's fine, right? So this would be equal to the integral from, well, let's see, this is 1/4 r to the 4th. So 1/4 integral from 0 to pi over 3, r to the 4th from 0 to 2, and then it just has a sine theta sitting there. Oh, it's sine squared theta. My fault. Sine squared theta. Sorry. So you definitely don't want to do theta first then, because sine theta is annoying. All right, so then d theta. So then I would put 2 into this, and I put 0 in. 2 in makes 16. So this is really 16 1/4 integral from 0 to pi over 3. 16 sine squared theta d theta. And of course we make maple do that because reasons. Maple. And we get, oh, and it'll be an approximation. This isn't going to be anything nice. So let's see here. Let's look at the integral work for part B. There we go. 1.228. There it is. Okay, so let me write 1.228. Now, that's not the whole thing, so I'm not going to circle it because it's not the answer. Now I've got to find the section for part B. And I'm going to give myself some space here. So let's do part B over here. And I'm going to have to work sideways. All right, so the volume, it's not volume, so the double integral, it probably is a volume, but it's r squared, well, it's still the same thing, right? This is still r cubed sine squared theta. This isn't changing for this next section because it's still y squared. That's still our integrand. So that piece I can kind of skip over and say, look, it's r cubed sine squared theta. But the dr and the d theta are different. So dr and d theta. Now theta is probably easier to see. It's going from pi over 3, chug, 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 to the end, which is pi over 2, right? So this is pi over 3 to pi over 2. R is going from 0, and then it's hitting this circle. This circle is 4 cosine theta. So it's going from 0 to 4 cosine theta. Okay, then we're just going to integrate again. So we're still integrating with respect to r first, so that's no problem, right? We already did that. It's just going to become 1/4 integral from pi over 3 to pi over 2. And then it's going to become r to the 4th from 0 to 4 cosine theta. And then it's multiplied by sine squared theta d theta. Right? The integration's the same, right? At least so far. The last integral will not be the same because these were constants up here for r. It was 0 and 2. This is not a constant, right? So I'm going to put in 4 into this and cosine theta. So that would be 256, right? So 256 cosine to the 4th. All right. So this equals 1/4 integral from pi over 3 to pi over 2, 256 cosine to the 4th of theta times sine squared of theta, d theta. And we are just going to make Maple do that. We are not going to figure that out. And again, it'll be an approximation. It will not be anything pretty. All right, so let's go look. And it's 0.362, right? And then you add them up, right? So when you add up 0.362 plus 1.228, and I actually added the exact answers and then had it do it because I used a labeling. So 6.2.1 was this answer, 6.2.3 is this answer, so I had it add them up, and then it gave me 1.591. So let me write this out. Of course, there's a little bit of rounding error, but we get the gist. So 590, 591, depending on whether you use the exact answers or not. But that's where you're going to end up. Oh boy, was that a lot of work. So let's pause there, and I'll see you in the next video for part C.